Sitting throwing rocks across the pavement, hoping they will cave in and swallow me whole. Wondering why my mind keeps on spinning. This isn't how living to me was told. Why am I like this? Something's always amiss. Can't put my finger on it, but it's there. Wait for it to subside, but my mind won't apply. Waiting for the clear. Is it bad sometimes? I like it when I lose control. There's something in it that's so beautiful.
Oh, okay, here we go. All right, hello, everybody. How is everybody doing today on this very fine morning or afternoon, wherever you're at? I hope everybody's doing well today. All right, we're here for Matho97 here today. Let me turn. There we go. Got it. Hey. All right. Hey, peoples, how are you doing, my friend? How are you today? I hope you're doing really well. It's been a good day so far. How is your... Oh, good. Yeah, very good. Very good. It's been pretty chill today, so relatively calm and cool and collected and all that stuff. Excuse me. Hopefully all kind of ready to go for some Matho 97. Oh boy. Nice and relaxing day today. It's been a crazy week already. Let's just hope we can all wind down, relax, and have a great time. That's what it's all about. Maybe not this material won't be the best thing ever, but hey, we'll work with it for what we got. All right, we're gonna get started here in just a minute, and we'll go ahead and get going after that. Yeah, okay. All right, almost to 10 o'clock here today. We're almost ready to go. So should be all right. All right, here we go. Excuse me. All right. Okay, let's get started today. Welcome back to Thursday, end of the week time today. So today, we're going to be we're going to leave off where we left off last time. We finished up chapter 1, talked about the syllabus and stuff. How long will the class be today? Well, how long I don't okay. Yeah, I don't suspect it'll take too long, trust me on that. So, um I was, typically, just to let you know, I don't go like the full 2 hours and 45 minutes, or you know, usually we take less time there because some of the sections don't have a lot of material in it per se. So to be fair, Vera, it shouldn't interfere too much with your work there. So try and keep it as realistic as possible. So usually I take about, I don't know, an hour, hour and a half, if that makes sense. Hey, Tom, like new layout? Oh, good. Yeah, things are great, Tom. I hope things are great over on your side. Doing just fine. All right. So today we're going to pick up here with chapter 2. Let's pick up with chapter 2 here today. Let's go to the big screen here for just a moment. All right. So bada bing, bada boom. All right. Oops. Put the other one up. Whee! All right, there we go. All right, so here is our. We're going to go ahead and start here with chapter 2 here today, is what we're going to be starting with. All right, and what is chapter 2 going to entail? As you can tell here on the screen, chapter 2 is going to be entailing working with fractions. So today we're going to talk about, kind of the basics of fractions, because we're going to see a lot of fractions here. I know nobody likes fractions. I totally get it. All right, nobody likes fractions, but we got to work with them nonetheless when we work in the trades in some capacity. Uh, and of course, we're going to be working with the first two operators of fractions here today, which is multiplication and division. Okay, so we'll talk about multiplication and division of fractions, and we'll also talk about the basics of fractions before we do those two things. All right, so let's go ahead and get started with that here today. All right, so first and foremost here, let's talk about fractions. Let's talk about what fractions are. Okay, so chapter 2 talks all about fractions. So section 2.1 is the basics of fractions. So all we're going to do here in this particular case is first talk about and say, okay, well, what is a fraction exactly? What parts are fractions exactly? How do we work with fractions? All right, well, let's take a look at some of the basics here, and then start working our way up with some of the key definitions behind that. So yeah, we'll come back to that. All right. So one of the things about the basics of fractions is, as we know here, what does a fraction generically look like? A fraction generically looks like it has one number on the top and one number on the bottom, okay? Or like an A over B kind of scenario. Now, one of the things about fractions, of course, is we have formal names for the top part and we have a formal name for the bottom part. I'll be kind of interspersing between the two here, but, it is what it is. All right, so the first part here is the top part here, which we would call the numerator. And the bottom part here is, maybe in text, all right, is the denominator. Okay, so we have a numerator and we have a denominator here. So A being on the top would be the numerator, and the denominator here would be the bottom. All right, so that's essentially how we can, put every fraction is going to look something like that in some capacity or form. All right, seems fair. All right. No problemo. Easy peasy lemon squeezy. Now, thing is that what we're going to look at here with fractions, of course, we need to know how to work with them, manipulate them. But what we need to know is at least, different looks about what fractions can look like in a realistic setting. So there's different ways that in a realistic setting that fractions could look like here if you're going to work with them in the easiest way possible. So a lot of the times I'll try and find the laziest way possible, and sometimes find the laziest way possible. To do that, it actually just requires, just to change your perspective a little bit. So how does that actually look like here? Well, let's take a look here at a couple of types of fractions here right away. First one here is let's talk about a proper fraction. All right, so what exactly is a proper fraction? Proper fraction is when the numerator is less than the denominator. So when the numerator is less than the denominator, that's going to be what we call a proper fraction. All right, and so these are pretty common. So what are some proper fractions? So examples of proper fractions could be, say, 5 over 6. All right, there's an example of a proper fraction. The numerator 5 is less than the denominator, which is 6. All right, or 7 over 10, okay, or 8 over 17. All right, all those sort of things are proper fractions, very simple to work with, easy peasy. All right, no problem there. A lot of the times we see proper fractions in some capacity or form when we're working with these problems. So you'll see them. You'll be like, yeah, there they are. Yeah. All right. So, all right. In any case, let's move on. All right. Next. Next is the other type of fraction which we're going to be working out with quite often as well, which are improper fractions. Now, improper fractions is a little bit different. All right. So improper fractions is when the numerator is bigger than or equal to the denominator. Okay, so when the numerator is bigger than or equal to the denominator is going to be what an improper fraction is. So what are some examples of improper fractions? Well, some examples would be, say, 5 over 2, or 7 over 3, or 8 over 8. Okay, those are examples of improper fractions of some variety. Okay, so the numerator here is bigger than or equal to the denominator. Okay, so the top part is bigger than or equal to the bottom part there of the fraction. I promise you that, not too hard. All right. All right. Easy peasy lemon squeezy. Okay. Are there any questions so far about that? I don't think that's too hard, but any questions so far? If you don't have any questions, just type no in the chat. If you do have a question, please go ahead and type out your question. No? Okay. All right. Easy peasy. We'll move on then. All right. So the question is that, well, we have proper fractions and improper fractions. All right. So what do we do with, say, these proper fractions or improper fractions? Well, let's take a look here at the last type of fraction that we'll see in many different types of problems, and those are going to be mixed numbers. All right. No? Okay. Now, we could talk about mixed numbers here. Mixed numbers here is definitely going to be one of those things that we're going to see a lot of. We're going to want to manipulate mixed numbers into a different form and then calculate stuff out with that. Now, how does that exactly work? Let's bring up our paint tool here. about mixed number. Let's bring up our paint tool here. All right. Now, first and foremost here, let's take a good look at our at mixed numbers here. So mixed numbers. All right. So with mixed numbers here, let's go ahead and put down an example here of mixed numbers. So the first example here of a mixed number would be, say, 3 and 2/3. Okay, so this is an example of a mixed number. Or again, 5 and 7/10. Okay, so this is an example of a mixed number as well. Again, there you go. All right. So all of these are both of these, as you see here, are examples of mixed numbers. And what we want to do here is a mixed number is we want to go ahead and convert from improper fractions into mixed numbers or vice versa. So that's what we're going to look here is saying, how do we start with, say, mixed numbers and go to improper fractions, or go from improper fractions into mixed numbers? All right, so let's take a good look at that and see how that's going to work out. Okay. The first thing that we're going to look at here is, let's go ahead and do that right now. So let's go from improper fractions to mixed numbers. Should I do, yeah, you know what? I'll do improper fractions to mixed numbers. That's fine. Okay, so let's do improper fractions to mixed numbers. Let's see how that's going to work out. All right. So it's not too hard to figure out how that's going to do, but let's talk about the big key behind this here. The key is to basically do regular division using remainders. So if you remember the super old school division here of just dividing stuff out, all right, if you're just dividing stuff out and you have remainders, that's what we're going to do here. So we're going to do super old school division just to get that to work out. So what is that going to look like here? Well, let's take a good look here using our handy dandy paint tool here. Okay, so let's start off with an example here, and let's see exactly what we're working with. All right, let's go with 17 over 3. Okay, so let's go 17 over 3. We want to convert this improper fraction into a mixed number. All right. So the first thing that we're going to do here specifically is we're going to just rewrite it. Remember, 17 over 3 can be rewritten as, say, 17 divided by 3. So maybe that if you know, remember, it can be written as 17 divided by 3. Now you don't have to do this every time, mind you. This is just for the sake of the example. But this is how I'm going to approach the problem. Now if I write 17 divided by 3 here, I'm going to actually just do old school division. If I just do old school division here, hey Aiken, how you doing, buddy? I'm doing great. How are you? If I do old school division here, 3 goes into 17 5 times. I take 5 times 3, that's going to be 15. And here I take 17 minus 15, which is 2. And that's going to be our remainder here at the end of the day. Remember, I don't want decimals here in this case. I want just remainders is what I want here at the end of the day. That's all good. It's all good. Today's the basics of fractions here, Rob. It's good to see you, by the way. Good to see you too. You and Aiken and everyone else. You guys are awesome. All right. So, how do we go ahead and express our answer? All right. Well, let's take a good look here. Notice that in mixed numbers here that we saw from before, like again, we had a big number here. Okay, so for mixed numbers here, if we were to write it out, just as parts here, you have a large number here, and then you have the actual fractional portion, like so. You have a numerator and denominator. Now, all mixed numbers are going to look like this of some variety. Okay, so that's what every mixed number looks like. So the question is, what parts are what here at the end of the day? All right, so this number here, this 5 that we got here, after we divided out the 3, this is going to be our big number right here. That'll be our nice big whole number here. All right. Next is going to be the numerator here of our fraction. And as it turns out, the numerator of our fraction here is going to be 2, the remainder that we got from before. So notice I'm just kind of drawing arrows to where they need to go in very particular spots. And then finally, the denominator here is going to be exactly what you divided by, which was, in this case, 3. So in this case here, 17 over 3 can be rewritten as 5 2/3 just by doing the simple division that we had here using remainders and stuff. Okay, are there any questions about that? I can do another example. So we'll be looking at this quite often, so getting comfortable with this idea will be very important. Any questions at all, guys, so far? Nope. Okay, perfect. All right, let's go ahead and do one more here, and then we'll do the other side here. Let's try that one. Let me make one up here. I'll put it up here. Let's do, okay, let's do 95 over 6. Let's do 95 over 6, and we want to write that out as a mixed number. All right? So here, we're going to put a 6 on the outside. Put 95 on the inside here, just doing old school division. All right, 6 goes into 9 how many times? How many times does 6 go into 9? How many times does 6 go into 9? You guys can answer, it's fine. Or I can wait, it's fine. It's an easy answer though, so I'll wait. 1. All right, good. All right, so it goes in 1 time, right? Simple enough. So we do 6 times 1, which is 6. All right, we take 9 minus 6, which is 3, down the 5. And 6 goes into 35 5 times. So 5 times 6, which is 30. That'll leave us with a remainder of 5. So then if we go ahead and put this together here, we get 15 as our dude. All right, so here we got 15. There we go. All right, and we got our numerator here, which is 5. 5 here. And then finally we got 6 is what we divided by here. Divide by here, that's going to be our denominator. So 15 and 5, 6 is going to be our answer here for that problem. All right. Easy enough. Hopefully not too bad. All right. Good stuff. All right. Any questions hopefully about that? Hopefully that's not too bad. I don't find that to be difficult. Um, but we will be using it quite a bit here. So, all right. Now, let's look at the next part here. All right. So this time here, let's talk about going the other direction here. Let's talk about mixed numbers into improper fractions. Now, in this case here, mixed numbers into improper fractions will have a little bit of again, also a method here. We just need to follow a particular formula here in order to actually go ahead and convert mixed numbers into improper fractions. All right, so let's go ahead and do that right now. So to do that here, here's what a mixed number generally looks like. We have A, which is the big number, B, the numerator, and C, the denominator. Now, if we want to convert that into an improper fraction based on what we see here with A, B, and C, then all we have to do is this. What we're going to do is, to get the numerator of our improper fraction, we're going to do A times C plus B for the numerator. All right. And then we're going to put that all over C for the denominator. Okay. So this is our generic kind of formula here. Add that to the notes there. So this is our generic formula that we're going to use to convert mixed numbers into improper fractions. So let's take a good look here at this, all right, and see exactly what to work with when it comes to numbers. All right. Okay. So first and foremost here, let's go ahead and do some examples, and we'll see how it works out. All right. So hello, Toki. How are you? I hope you're well. Let's try 4 and 5/11. All right. Let's go ahead and take a look here at 4 and 5/11. So what we're going to do here is we're going to take A times C. So we're going to take 4 times 11 plus 5. And we're going to put that all over 11. So here we got 4 times 11, which is 44. We add 5 to that. So here we get 49. That's going to be put over 11. All right, and that's it. 49 over 11. That's your final answer at the end of the day. Easy peasy. Let's try one more here really quick. Try 2 and 5/16. All right, so in this case here, just going to take the 2, multiply that by the 16, add the 5, put that all over 16. 2 times 16 is 32. 32 plus 5 is 37. We get 37/16. All right, that isn't too hard there. There we are. Should be pretty relatively straightforward. And there you go. You got yourself a winner chicken dinner. All right. Now, this is pretty important because of all the other things that we use this for. These conversions make life like 20 times easier. Am I a university teacher? Well, I teach at a community college. I don't know if that's not technically the same thing as university, but yeah, I am a math professor. Yeah, that part is true. That part is definitely true. Been math professor for a decade. Yeah. Yeah, it's pretty fun, right? Absolutely pretty fun. All right. Let's talk about the next thing here. Let's go ahead and discuss the next part here. All right. So, with fractions here, one of the things that we'll talk about when it comes to fractions and the basics of fractions is we want to talk about, again, finding equivalent forms of fractions. And this is going to be especially helpful for, say, adding and subtracting of fractions, which, in my opinion, adding and subtracting of fractions is by far the toughest thing that a lot of people have trouble with when it comes to fractions. Multiplication division is not so bad. But really, what it comes down to is it really comes down to the adding and subtracting part. That's really the toughest part here. Now, in order for us to kind of understand that, how do we exactly work with that here? Well, let's go ahead and find out this next part here. Now, go ahead and take a look here at some examples of finding equivalent fractions. So let's say we're given an example here, and we're um, given say 3/8 is equal to something over 32. Okay, let's say 3/8 is equal to something over 32. Now, by and large, this isn't too hard, but one thing that I do want to point out here in regards to this example, in math, there's certain examples that are really easy, but actually have more importance than and more advanced examples. Let me show you why this is one of those examples that certainly has probably a lot more importance than what it really looks like. Now, the numbers by itself aren't really the important part here. The important part here comes down to the actual process itself. The process here is what really drives everything. And this is something I'm going to stress a lot on in future chapters here. This is why I kind of stress on this particular problem. Now I say, hey, I want to go ahead and find out what this number is right here. And there are multiple ways to do it. But one of the ways that we can do this is basically figure out how many times 8 is into what do we have to multiply by, like multiply 8 by to get 32. That's essentially what we're looking at here. So, you know, So let's go ahead and find out what that is. Alex Ford, how are you, my friend? I hope you're doing well, my dude. So 8 times what is equal to 32? Can anybody tell me here? What is 8 times what equals 32? Let me know. What's that question mark part there? What 8 times something is equal to 32? What's that number there? I'm very good, Alex. Very, very good. It's been a really fun and exciting day already. 4. That's right. So, one thing that we could take to the bank here is that if we have to make this 32, I have to multiply this 8 by 4. Now, what's the big key here? The key here in these problems is something that we're going to talk about quite often here in future chapters. And this is especially true in algebra. So it's always good to start early so that way you understand how big of a deal it is. The key is to multiply or divide both the numerator and denominator by the same number. One of the things in the key to algebra, okay, and I will be repeating this very often, If you ever have a trouble with algebra, I'm just going to state this now. What's the biggest key to algebra? It actually, um, can you do the butterfly method? You can, but I want to point out one thing here, Vera. I mean, you could do the cross product method, and that's perfectly fine. The butterfly method works fine. But one of the keys that we'll talk about here in algebra, where the butterfly method can't work, and why I actually use this method for a lot of things, is it makes the math significantly easier if you're trying to do it in your head. And this is kind of like why I'm stating it now, and then we're going to see this later on. The key to algebra here is to basically, it all comes down to the word balance. And this is one of the first keys that you find out here. Like the butterfly method, for example, is one version of balance in one situation. However, in algebra, you see a lot of different other types of problems, and we'll be encountering different types of problems here later on as the course goes along. So, when you understand that it comes down to that word of balance and you're not always just multiplying the top and bottom, no, you're actually balancing things out in different ways when it comes to like doing an algebraic concept. And at least understanding that now, at least in this term, a fractional concept, yeah, that makes perfect sense to doing the cross product or butterfly method. Makes perfect sense to me. All right, but my big key here comes down to the word balance. Balance makes things significantly easier. I learned understanding balance here, it made doing the algebra and doing the math really, really simple. Once I was able to get that process down, if that makes sense. So here we get 12 over 32 here, with 12 being our answer here with 3 times 4. Balance here is going to be the biggest key. So what we do on the bottom is what we do on the top, or what we do in algebra here, what we do on one side of the equation is what we do on the other side of the equation. A lot of algebraic concepts, even if they're super advanced, come down to that point right there. But I'm not gonna say you're wrong there, Vera. Not at all. For this problem, anyway. Let's go ahead and try one more here. Let's try. That's a 5. Set up. Ah. Whoops. Let's try that again. Not look dumb. All right. Okay. All right. The question mark. All right. Okay. So here's a mixed number and a fraction. All right. Now you can't do it straight away. I mean, it looks like you can brute force it, but really you have a mixed number and a regular fraction. So if you have like a mixed number and a regular fraction, one of the other things that we'll talk about here is typically, um, let's talk about the key to working with mixed numbers. Uh, Typically, we change the mixed number to an improper fraction to do calculations with. So, oh my goodness, it is James Hodges. How are you, Mr. Hodges? I can't believe the legend himself is in this chat. I don't believe it. What's good? I'm doing fractions and mixed numbers today, my dude. If you can believe that. How are you? What are you doing? Are you doing marbles on stream? Some COD? Hey, fun times indeed. You know, one time I'm gonna be honest with you, James. I'm gonna be honest with you, James. I'm gonna get over there. I'm gonna get over there to your house. Okay, James? I'm gonna get over to your house. I'm gonna teach you some math so you know how to get better at COD, okay? And how, more kills in COD is better than one death, okay? That's important math. It's a very important math. we need you better. Also, points in Scriblio. That's very important, okay? You need to have more points, okay? This is the important part here. I know the math. The math is true. Okay? It's true. So, James, let me ask you. This James. James is a very valued member of the stream, okay? James is a super valued member of the stream. So valued, in fact, that I'm modding James right away. So, no, James is a very valued member of the stream. James is a great guy. James has the best super positive attitude. James has the best super positive attitude I've ever met. I don't know what else to say about you, James. You are a very positive attitude. That's why I love coming to your stream. Doesn't matter how big stream is here on Twitch. You have like one of the best positive attitudes I've seen. And I know not everybody's positive all the time, but I like your aura of optimism and just overall enjoyment of doing things. That's really genuinely that's what makes it fun coming to your stream. You legitimately are one of my favorite streams here on this platform. Absolutely. So I wanted to tell you that at least first and foremost, for coming on the stream here. I'm gonna call you out just based on that alone. A genuine guy, James M. Hodges, 100%. Yeah, James has his own stream, by the way. He plays COD, he plays Scriblio, he plays Marbles on stream, he plays a whole bunch of things. He put eggs down his pants, whatever you want. That's James M. Hodges for you. There you go. James Hodges. The man, the myth, the absolute. James, you're a bigger legend than I am. I'm going to tell you that right now. I think everybody's a bigger legend than I am, but you, my friend, definitely, I will effuse your praise. It's true, the egg was no fun. All right. Math problems. So, James, can you answer this for me? I don't know if you can, but we're gonna test you. We're gonna ask. No, man. Trust me on that. I'm just a guy. So, James, do you know what 3 3/5 equals to as an improper fraction? Here's a good math. Actually, what's 3 3/5 as an improper fraction, James? What does that equal? 3 3/5 is an improper fraction. Let's go back to your levels. Yep. Let's go back to your levels. All right. Chase Murphy, my dude, how are you? Wow, great to see you, buddy. I hope you had a great winter break. Made honors after all. Oh my gosh, really? That is awesome. Great job, dude. Me? Nah, man, you really worked really hard last semester, Chase. I'm very proud of you. Very, very proud of you. You're confident taking on trigonometry? Look, Chase, if you got questions for trigonometry, please feel free to ask, okay? You know what my email is. You can just feel free to email me and I'll be happy to clear stuff up for you. I've taught that class many times. So again, if you need help with whatever, please feel free to ask. I'm really proud of you though, Chase. Congratulations. That's awesome for getting honors. James, I haven't heard an answer from you yet. 3 3/5. 3 3/5 as an improper fraction, my dude. Chase, you should meet James. James is a legend. Not a clue. Okay. Let's go over this again here. So we get 3 times 5. That's the denominator there. We're going to add the 3, which is the numerator, over 5. So you get 3 times 5 here, which is 15, plus 3, which is 18. So you get 18 over 5. There you go. That's a 3 3/5, straight up. So here we got two fractions. We got 18 over 5 equals question mark over 10. All right. So we got to multiply 5 by something to get that 10. Well, what do we do? 2. All right. Good. And then I don't have to tell Rach, things that happened today. I'm just saying. Hey, no problem, Chase. Feel free to contact me anytime, okay? I'm here to help. Oh, why'd I put 2 there? I don't know why. Anyway, so we got 18 times 2, which our final answer here is going to be 36 over 10, which is the equivalent fraction that we have here. All right, and there we go. We got it. Simple enough. All right, so 36 over 10, our final answer for that problem. All right, not too shabby. Okay, next, let's do the next part here. All right. Yeah, nice job, man. Let's write fractions in lowest terms. This is basically, instead of multiplying, we're now dividing. So that's the key here. The key here is pretty easy. The key here is to divide by the same number on the numerator and denominator. Give you the hardest problem. Tokyo give you the hardest problem. Okay. All right, let me give you the hardest problem for this. And let's see if you guys can get it. All right, I think that's fair. You guys want a challenge? We can do that. All right, so let's take a look here at some of the tougher ones I could come up with here. All right. Let's go with this one at least to start with. Maybe a slight warm up. Let's go with 38 over 24. We want to write that in lowest terms, meaning to say what we want to do is we want to have a number that divides both the numerator and denominator. Okay, so one number that's the same, it has to be the same, right? Because everything's balanced. So we have to divide, what number should we divide by for 38 and 24? Again, if you're not sure, it doesn't have to be a big number. It could be a simple number. And then you could just go ahead and work with that. So what do you guys think? What do you guys think? What do you think we should divide by here? 38 and 24 might have one number in common that we can divide by in both cases. 4. Now, I agree 24 divided by 4 is definitely going to equal a nice, clean, whole number. But does 38 divided by 4, is that going to get us a nice, clean number? Okay, 2. Yeah, unfortunately, 4 doesn't work for 38. You have 9 times 4, which is 36, and then 10 times 4 is 40, so unfortunately it skips 38 in the process. And again, if it takes you a little trial and error, that's perfectly fine. So, right. So if it takes you a little trial and error, I'm not going to criticize you. That's it. Just sometimes just start off with something simple, right? If you see that, for example, here, this is both. These are both even numbers. So if they're both even numbers, you could just go ahead and be like, okay, let's just divide by 2 to start with. Just do it in steps if you need to. You don't have to do it all at once. So one of the things that is understandable is like, hey, I don't need to get it done all at the same time. I can just do it one step at a time until I get 2 numbers that don't have anything to do with each other. Like in this case, if you did 38 divided by 2, you get 19. And 24 divided by 2, which is 12. And then there you go. Then we take a look at our resulting answer, see if we can go further. So I'll make a note about this here. Note. Reduce further if you can. I should say if necessary. That's probably a little bit more appropriate. All right, so 19 and 12 don't have anything to do with each other, so this is where we stop. A lot of the issues that people have with math is like, how do I know where to stop? Well, this is a good place to stop because nothing, not at the top or the bottom there, the numerator and denominator, have anything to do with each other in terms of common factors. Okay, let's go ahead and take a look at another one though, and let's see that in action, shall we? All right, let's look at uh, true. All right. Dividers is denominator? Right. So Tokyo, just to put it here, the top number here is going to be the numerator, and the bottom number here will be the denominator. Heading out, James? All right, my friend. Hey, you have yourself a wonderful day. If I see you on stream, then I'll pop in to say hello myself. All right? Get your work done, man. Thank you so much for popping in, okay? I really appreciate it. Thank you so, so much. That's really super kind of you, dude. Yeah, you have a good one, okay? I'll see you again, all right? Thank you, my friend. All right. Let's go ahead and take a look here at let's see which other one I wanted. All right, let's do that one. Yeah, that's fine. Let's look at 28 over 56. Okay, let's look at 28 over 56. So in this case here, let's go ahead and see if we can reduce this down. What can we divide by on both the numerator and denominator? So on the top or the bottom, top and the bottom here, we have to divide by the same number here. What number can we divide by here in this case? What do you think we got here? Let's start off with a simple number here. Okay. Notice we have 28 and 56 here. We can divide both of those by 2. Let's start off with something simple. Okay, we don't have to go for everything at once. Oh, you want to try 4? Okay, we try 4. We try 4. That's fine. 4 works too. I don't mind doing 4. We do 4. That's actually true for this case. All right, so if we do 28 divided by 4 here, we're going to get 7. We do 56 divided by 4 here, and we're going to get, what are we going to get here? We're going to get 14. Okay, so absolutely 100% correct. Now, we have 7 over 14 here, which is right. Now, can we divide by anything else? We could take another step if we need to. Does 7 and 14 have something in common we can divide by? Hmm, 6? Not exactly. 7 divided by 6 doesn't equal a nice number here. But 7 and 14 do have something in common. Don't forget, Tokyo, here, that you can also divide by yourself. Remember, we can divide by 7. 7 can divide itself, and 14 divided by 7 is equal to a whole number as well. So we get 7 divided by 7, which is 1, and 14 divided by 7, which will be 2. So in fact, if we look at 28 over 56, that's going to be equivalent to 1/2 at the end of the day. Yeah, exactly. All right. Are there any questions about reducing fractions and whatnot? Obviously, this just requires a little bit of practice, so it's totally understandable if you don't get it right away or you have a tough time with it. The point is that it just takes a little practice and a little bit of getting used to. So, no, okay, great. Okay, now we have one more thing to talk about here, and then we'll look at one word problem in here, and then we'll move on here. A lot of the setup for this entire chapter really is this first section, at least understanding these fundamentals behind fractions. All right, now last major concept here before we look at some word problems here is comparing two fractions. So some problems here talk about, okay, well, which fraction is bigger? And they give you like two random fractions, and you're like, well, I don't know what number, which one is bigger because they both kind of look the same. So it's like, okay, well, how do we determine exactly what that's going to be? All right, let's take a good look at that right now. 28 over 7 and 56 over 7. Yeah, that's correct. Yes. You could use 7 as well to start with, Tokyo. That is correct. That's absolutely correct, Tokyo. Totally agree with that. Like I said, there's more than one way to kind of do those type of problems. So if you want to do it that way, I'm perfectly cool with that. If it helps you see how the problem will work out, perfect. Because with math, you could do it many different ways. There's many problems you could do many different ways. So I always tell people, just because I show one way here on the stream doesn't mean it is necessarily the way if there's an alternative way that you're more comfortable with. So do it in a way that you're comfortable with, and that's going to work for you. And as long as it's consistent in terms of the process, I'll be very happy with that. Very, very happy with that. So we want to see which one of these fractions is bigger. Is 3/5 or is 4/7 bigger at the end of the day? We want to determine which one is bigger. Now, they both look pretty close. You could say, well, they're both over a half, and be like, yeah, they're both over a half, but by how much? Hmm, okay. Now, there is a definitive way to go ahead and compare two fractions together. So let's take a good look at what they are. In this case here, it doesn't look like they have much in common. Not yet, anyway. What we need to do here is talk about the big key here, which is going to help us with the last section, especially here for this chapter. And the big key here in this particular case is to find a common denominator. So we're going to find a common denominator. Now let's talk about what a common denominator is. All right. A common denominator, sure. A common denominator is a multiple, is basically the smallest multiple of all the denominators. Uh, Smallest multiple in common between all of the denominators. Okay, so that's correct. We're going to see exactly how we can justify that, but you're correct there. That's absolutely right, Tokyo. All right, so the smallest multiple in common between all of the denominators. Now, I do want to point this out here because this is going to be important for adding and subtracting. So this is like one of those examples that doesn't seem like it has a whole lot, but it has a lot more meaning to it. Now, one of the things I want to kind of point out here says the smallest multiple in common between all the denominators. Now, I'm going to put a big note here. Um, the common denominator, I'll put CD for short. The common denominator will always be the largest denominator or bigger. Okay? So one of the things that people are confused about is, well, if I had a common denominator here, this is what I get very often, as I see people say, okay, well, tell me what's the common denominator between 3/4 and 1/2, and then they say 2. 2 is the common denominator. And then I would say, well, no, that's not true. You have to actually start at 4 and then work your way up, because again, the key here is that it's the smallest multiple. All right, so it's the multiple. It's not like what divides both numbers. So 2 is not a common denominator. It's actually 4 here that's actually your common denominator, because that's the biggest denominator, and 2 divides 4 and 4 divides 4. So just be very careful about that. I'll probably reiterate that again, but I'm just letting you know about that now. So in this case here, as Tokyo has correctly pointed out, the common denominator here is going to be 35. Okay. Again, we start at 7, and then we work our way up from 7. So we say, okay, does 7 divide 7, obviously, so that's fine. But does 5 divide 7? No, so that can't be it. I try with 14. All right, 7 is going to work with every one of these numbers. I'm just taking the multiples of 7 here and working my way up. 14, does 5 divide 14? No. 21, all right, 5 does not divide 21. 28, 5 does not divide 28. All right, and then I get to 35, and then I say, oh yeah, okay, well then that works. 5 definitely divides 35, so that's my winner. Okay, so I'm taking the multiples of the largest denominator and then just working my way up from there and making sure every other one of those denominators divides that evenly. Now, in this case here, um, since we want a common denominator at 35, on the bottom here, we want 35 to be on the denominator here. And just like what we had for the finding equivalent fractions, we're going to do the same thing here. We're going to balance. So again, we have 5 here. We're going to multiply this by 7. But if we multiply the bottom by 7, we got to multiply that top by 7 as well. Okay, everything is a balance. Same thing here with 7. We're going to multiply that by 5. And then we're going to multiply that top part by 5 as well. And then as we can see here, we get 21 over 35. And then we get 4 times 5, which is 20, over 35. And so as we can see here, 21 is bigger than 20. So this is going to be our winner, since this is clearly the bigger of the two numbers. And there you have it. That's how we can determine which one of the fractions here happens to be bigger. Okay. Let's try one more. So this will be a quick one. Okay. Can anybody tell me here, what is the common denominator? What's the common denominator of 7/8 and 5/6? What's the common denominator between 7/8 and 5/6? 48, that's close. 48 would be in common between 8 and 6, but there possibly could be something smaller. Remember, the common denominator is not always taking both denominators and multiplying them together. Remember, it's a multiple of both numbers, which could be smaller than 48 in this case. Let's start off with 8. Now, does 6 divide 8? No, 6 doesn't divide 8. Let's try the next multiple up here, 16. Does 6 divide 16 evenly? Nope, not true. Let's try the next one up here. 24. Does 6 divide 24 evenly? The answer is yes. 6 does divide 24 evenly. So here we're going to have 24 as our common denominator here in this instance. Yep. So hopefully that makes sense there about how I found 24 here in this instance. So again, I'm starting from the largest denominator and then working my way up, right? So that's why I'm not going to make an assumption and be like, oh, it's always going to be like, multiplying these numbers together. That's not true. You have to be a little bit careful about that. All right, now we're just going to multiply this by 3 to get 24. We're going to multiply this by 3 because we got to balance things out. And then here we have 6 times 4, which is 24, and we're going to need to multiply that by 4. So here we get 21 over 24 for the first fraction. And for the second fraction, we get 20 over 24. So we can see which one's our winner here. Our winner is going to be the first fraction here, or 7/8. Okay. And there we have it. 7/8 is bigger than 5/6. All right, good stuff. All right. Now, we've taken a look at a lot of the basics here for fractions. So let's take a good look here at an actual book problem, finally. I know it's been a while, but let's go ahead and do that right now. All right. So I'm just going to do one of these, and then we'll move on to the next section here. So, because I know people have schedules and whatnot, so I'll try and make this next part a bit quicker for you. All right, let's go ahead and take a look at one of these problems here. Printing. All right, so a printer has 15 rolls of newsprint in the warehouse. What fraction of this total will remain if 6 rolls are used? So we have 15 rolls of newsprint in the warehouse. What fraction of this total will remain if 6 rolls are used? Okay. So for this particular problem here, we start off with 15 rolls and we use 6 of them. All right. So that's fair. So what we need to do first is we have 15 rolls and we're going to subtract 6. So we have 9 rolls left in the warehouse. So that's one thing you have to be a little bit careful about is that, yeah, we use 6 of them, but this is one of those problems where you have to like read the problem really carefully. So for example here, it says, in this case here, the printer has 15 rolls. What fraction of the total will remain? So the key word there is what will remain if the 6 rolls are used. So be very careful about the wording of the problem here. It can be fairly deceptive if you're not careful. We have 9 rolls used here. So we have 9 over 15. We have 9 rolls that are unused over 15. We go ahead and reduce this down. We're going to divide this each by 3, since 3 divides both 9 and 15. And so finally we get 3/5 as our final result here. Okay. So 3/5 is our final answer for this problem. All right. Not too hard here, but there we go. All right, good beans. All right. So that's kind of the one example I kind of want to show off here, but a lot of this in this particular section really is just getting these basic fundamentals up, because then the next few sections here will make a whole lot more sense. and it'll be a lot easier to work with once you know the ideas behind it. Plus, we'll see this over and over and over again in a lot of different problems. So we're going to want to have um, this case here. You don't understand the problem's question. Okay. So in this case here, the printer has 15 rolls of newsprint in the warehouse. What fraction will remain? So we use 6 rolls here, okay, Tokyo? We use 6 rolls here. So that means we have 9 rolls left over when we do 15 minus 6. Okay? So we want to find out how much is left over. Again, how much will remain? How much will be left over? So 9 rolls will be left over at the end of the day. So basically it says, well, we have 9 rolls out of the original 15 rolls that we had in the warehouse. And they just want us to go ahead and reduce that fraction down after we figure out how many rolls are left in the warehouse. And that's exactly what we did here in this particular problem. All right. So that's how we're able to kind of put those two together there. So again, just read the problem very carefully. Yes. No problem. Definitely will acknowledge your question. Absolutely, 100%. Yep. Okay. Let's go to the next part here. All right. All right. So the next couple of sections here should be relatively quick compared to the other two. So compared to this first one. All right. So let's talk about multiplication of fractions. Okay. Let's discuss multiplication of fractions. Now, multiplication of fractions is going to be one of those things that isn't too hard to do, because all you got to do here to multiply with fractions is a very simple process here. If you have two fractions, let's just put generic letters for fractions. Let's do a times b times c over d. Well, all you got to do is multiply straight across. That's it. You multiply a times c on the numerator and b times d on the denominator. And bada bing, bada boom, you got yourself a winner. So by far and away, multiplication is the most straightforward of the processes that we ever encounter when it comes to fractions. However, there is one other thing that we do need to take into account here. One of the biggest issues about multiplication is it's very, very simple to get very large numbers very, very quickly. Okay, especially with multiplication, as you know. So the key here, what's the big key here into doing multiplication with fractions? The big key here that we're going to be focusing on is not so much the rule. We are going to use the rule, of course, but is basically going to be reducing the fractions before we multiply across. Okay, so that's going to be the key here, is that we're going to want to reduce these fractions before we multiply straight across, and then we're going to end up with our answer here. Now, let's discuss a couple of these problems here, because well, actually maybe one of these problems certainly I need to do in terms of just regular numbers, and then we'll look at another one here. So pages 90. Tokyo, thank you for the follow, my friend. All right. Um. All right. Let's do a simple straight up multiplication problem here, and then we'll see what we're working with here. Well, some people often get confused that it's always going to be what it's divisible by. So when people see the word smallest, they always look at the smaller number first, as opposed to the larger number first. So That's a common mistake when it comes to finding out the common denominator. It's a very common mistake I see quite often, no matter what level of math actually people do. So, um, really, you could be doing a calculus class, and I see people making the same mistake. So again, I always stress it's always the largest denominator or bigger, because when they see the word smallest, you kind of tend to look that way as the smallest number. So it's just kind of human nature where it's like, okay, you hear a certain word and you kind of gravitate toward that specific meaning of that word rather than looking at it from a much just a direct point of view as opposed to what the point of view is supposed to be. So just one of those things you point out over the years that certainly people get confused about. But that's why I'm here to just kind of clear up those misunderstandings. So that way it's clear about what perspective you should be looking at the end of the day. Okay. Now you see some multiplication problems here. These of parts here are also multiplication problems. Of is another word for multiplication. Just pointing that out there. So of means to multiply. Of is just a very fancy word for multiply. All right, anyway, I'm going to do one of these particular problems here because they do have rather importance here. Okay, so I want to do, yes, that's a good one. So let's do this one here, 7/16 of 6, or again, in this case here, let's just do 7/16 times 6. Now I'm going to make a couple of notes here, all right, in regards to this, to make this easier to do. Hardest one, yeah. All right. First and foremost here, 6. All right, now this is going to be rather important. If you just see a whole number like 6, all right, or 5 or 7 or something, all right, 6 can be rewritten as 6/1. So one of the things you can do is you can rewrite that particular guy as, say, 6/1, or 5/1 if it's 5, or if it's 10, it's 10/1. This will make organization significantly easier. All right. And that is in the entire point is just to make things easier for your organization so you can see where the numbers specifically need to go in each circumstance. So here we have 6/1 instead of just 6. So all numbers are going to look like that at the end of the day. All right. So let's put a small note here as well. So note. Let's go with A is equal to A/1. So, all right. So you can just rewrite it just like that generically. And there you go. You got yourself. Okay. Good stuff. Now, having said that, like I said before, normally what we could do is multiply straight across. But we could do 7 times 6/16. The problem is that 7 times 6 is 42, and we'll get 16 times 1, which is 16. Problem is I don't want to deal with big numbers, okay? Oh, that's good. Good. At least it's giving you cleaning out the cobwebs, getting some reminders there. Um, so 7 times 6 is 42. We have over 16. I don't want to deal with really super big numbers. I want to reduce things down prior to doing the actual multiplication. Now, as long as we have one number in the numerator and one number in the denominator, we can reduce things down. So let's take a good look here in this example, and we'll see exactly where this fits in. So if you take a look at 6 and you take a look at 16, we have a pair of numbers. So let's put a second note here. So note number 2 here. As long as we have a pair of numbers, a 1 in the numerator, one in the top, and one in the denominator, one in the bottom, that have something in common, we can reduce. Okay? And those pair of numbers can come from two different fractions. Okay? So for example here, 6 and 16 have something in common. All right? We can divide 6 by 2, and we could also divide 16 by 2. So we divide 6 divided by 2, which is 3, and 16 divided by 2, which is 8. Now we go ahead and take a look and see, oh, is there anything else in common? Okay, do we see any other numbers we can reduce down? Well, 7 doesn't go with 8, so that's out. And 3, unfortunately, doesn't go with 8, so that's out too. 1 we're going to leave alone because 1 goes with everything, so it pretty much does nothing at the end of the day. So this is where we stop in terms of reducing things down. Now, once we got it down to that form, we go ahead and multiply straight across. So here we get 7 times 3 over 8 times 1. And so here we get 21 over 8. And if it does ask you to put it in terms of a mixed number here, the mixed number here is going to be 2 and 5/8. So again, just doing the division here. So if it does ask you on the homework problem, convert that to a mixed number, then you'll know how to do that. It's not too. Okay. So 2 and 5/8 is what we get there in that case. All right, good stuff. Okay, so that's how we can do that particular problem there. Let's go ahead and do another problem. All right, this time though, we're going to do a word problem. All right, let's do a word problem here. So pair of numbers will mean two numbers there, Tokyo. So Yusuf, how are you doing, my friend? So a pair of numbers here would mean two numbers. So this would be 1, 1. This would be 2. So this is a pair of numbers here, Tokyo. So those are the two numbers that have something in common there. Okay? You got it, buddy. Good, good, good. You're doing good. Good, my friend. Hopefully it's a nice, wonderful night where you're at. Or day, if it's still daytime. It's almost noon here, so, or not almost noon, but past 11, I should say. A little bit past 11 in the morning. Let's go ahead and do another here. Actually, I'll come back to this, see if I need that. All right. Okay. Let's do a word problem here, really quick. Okay, so let's take a good look here at this one. All right, so if a car averages 22 and 3/4 miles, 22 and 3/4 miles or 22 and 3/4 miles to a gallon of gas, how many miles can it travel on 14 gallons of gas? So in this case here, we have a mileage. Could be mileage again, miles per gallon in this particular case. Could be miles per liter too. So or kilometers per liter if you want to go and do the overseas thing, absolutely. But still, nonetheless, exactly the same. So here in this case, we're going to take 22 and 3/4 and multiply it by 14. Let's go ahead and do that here. Okay, so what is 14? We got to rewrite 14 here. So how can we rewrite 14? What would 14 be equal to? How do we rewrite that again? What does 14 rewrite to here? So we wrote 6 as 6 over 1. So what would 14 rewrite to then? In the meantime, we're going to do one other thing while you sit and I'll sit and wait there. We'll have to 14 over 1. That's correct. Dark Legend, absolutely correct. Very good, my friend. Nice. 14 over 1 is correct. Now we're also going to have to do one more thing here. Hey, that works for me. We're also going to have to rewrite 22 3/4 in terms of a improper fraction. And I believe that's correct, but let's just be sure. We have 22 times 4 plus 3. How you doing? How you doing, Dark Legend? Hope you're doing well, my friend. We'll put that over 4. We got 22 times 4, which is 88, plus 3, which is 89 over 4. That's correct. Okay. Put 89 over 4 here. Absolutely spot on. Now, is there a number that, let's take a look at a pair of numbers here that we can hopefully reduce by, because 89 over 14 is a pretty ugly number. Okay, so 89 times 14 is really ugly, so I don't want to deal with that. So let's see, 14 and 4 here. Let's take a look at that pair of numbers, because 89 doesn't go into 4. What can we divide out between 14 and 4 here? What can we divide out between 14 and 4? What do you think? 2. Sounds good to me. So let's divide out by 2. All right. So here we're gonna get 7, and here we're gonna get 2. So 7 doesn't go into 2, or 2 doesn't go into 7, I should say. So essentially, that's where we're gonna stop. So we're gonna have 89 times 7 over 2 times 1. So here we're gonna get here we get 63, and so we get 7 times 8, so that's gonna be 62. All right, so we get 623 over 2. And then we'll just go ahead and make that back into a mixed number, just in case if, say, the problem does ask us to put it as a mixed number. So go ahead and do our regular old division here. Do 623 divided by 2. You can use a calculator for this to find the whole number equivalent anyway, but you get 3. We'll bring down the 2 here. That'll be 1. And we'll bring down the 3 here. And that'll be 1 again. We'll get a remainder of 1. All right. So 311 and a half. What you learning now, Dark? I am kind of curious what you're learning in maths right now. All right, good stuff. All right, so 311 and a half here is going to be our final answer for this problem. All right. And that'll be, in this case, miles for this car. Okay. Let's go ahead and do one more. And then I'll get to division, and then I'll stop there. Length scale factor, length scale factor, area scale factor, and volume scale factor. So basically, if you're scaling a figure, correct? And then you have to do the proportions and stuff. Because I mean, that's not too bad to do proportions for that. Like if you have a 4:1 scaling ratio or something to that effect. Okay. Let's take a good look here at one more here. At all right. Good. Nice. All right. One more here for this section. Not sure that's going to be the hardest one. It's just a different way to look at things, however. Okay, 26. The center-to-center distance between consecutive holes in a strip of metal is 5/16 of an inch. What is the total distance x between the first and last centers shown in the figure? So here's the picture in question you can see here on the screen. Okay, and we want to find out what the total distance is between the first center, which is what you see this first line at, and the last center, which is this line, right, which is this little circular hole on the right-hand side. 1, 2, 3, 4, 5, 6, 7, 8. So it looks like in this case here we have eight distances of a 5/16 of an inch. So let's try that again. 1, 2, 3, 4, 5, 6, 7, and 8. Okay, so got to be careful about the picture there. You got to be able to at least read that off carefully. One of the tricky parts sometimes when you have a picture problem is you kind of take a few liberties, but why we just look at it and see what happens. All right. So here we're going to have 8 times 5/16. We're going to rewrite 8 as 8 over 1. And we'll multiply that by 5 over, excuse me, 5 over 16. Let's take a good look here and see if we can find a pair of numbers that we can reduce down with. So let's take a look at 16 and 8, since 5 doesn't go with 16. Can we divide 8 and 16 by a number? Is there something that 8 and 16 have something in common with? It's a number that I can divide out here. I can divide 16 by a number. I can divide 8 by a number, that same number. What number is that going to be? 8. That's right. Nice. So I'm going to divide by 8 here. We get 8 divided by 8, which is 1. 16 divided by 8, which is 2. Now we have 1 times 5 over 1 times 2. And so here we get 5 over 2. Or again, that'll be 2.5 if we need to convert that over. So in this case here, that's what we get here. 5/2 inches, or again, 2.5 inches would be our final answer here in this particular instance. All right, good stuff. So that's multiplication of fractions in a nutshell. All right. Now, so what I'm going to do here is I'm just going to briefly go over division of fractions here. I know that Vera, you had asked because of your time constraints there, so totally understandable. I can always pick up where we left off for division of fractions here, and then we get to addition subtraction here, which is definitely my plan here for next time. But I want to show off at least one example here for division of fractions, talk about the key, and then we'll reiterate that for Tuesday. So, okay. In any case, however, let's look at section 2.3. So section 2.3 is going to be division of fractions. All right. So division of fractions is going to be fairly straightforward once you understand the rule. Let's take a look at the rule here that we need to apply. So in this case here, let's take our two same set fractions here. Actually, start over. All right, there we go. And so here, we're going to go ahead and put the division symbol here. So a over b divided by, in this case, c over d. Now, unlike multiplication, however, we cannot divide straight across. Okay, we're not allowed to do that. Instead, we want to put it in a form that's a little bit easier to work with. And that's exactly what happens here in this case. Instead of doing division straight up as it is, instead we change it back into a multiplication problem once again. So going back to multiplication here, but there is a consequence for changing it to multiplication. Consequence is that that second fraction is going to flip over. So instead of c over d like it was previously, it is now d over c. So this is the rule here for dividing fractions. We change it to a multiplication problem, but with the consequence of flipping the second fraction. So that's the big key here in this particular instance. Key here is to flip, is to change to multiplication and flip the second fraction. Okay? That's going to be the important part here in this instance. So let's go ahead and take a look at how we can do that and see how this works out. All right, let's go and do it. So in fact, one of those things in this particular instance is a kind of a scaling type of problem here. So let's go ahead and do that here in this instance. All right. Ask and ye shall receive. All right. Here we go. We'll get to this Brook problem here. It says on page 98. Okay. So let's take a good look here at say, a drafting type of problem here, which is a kind of a scaling type of problem. It says if 1/4 of an inch on a drawing represents 1 foot. Okay, magic of math, you got that right. If 1/4 of an inch on a drawing represents 1 foot, then 3.5 inches on the drawing will represent how many feet? Well, in this case here, since we're given a specific proportion, in this case, I would say, okay, 1/4 of an inch is equal to a foot. Well, okay, how many feet are 3.5 inches on that drawing? Okay, if we, obviously, if you're making an architectural drawing, you're obviously not going to draw it to the actual scale of the house. You're going to obviously have to paraphrase it. This is, of course, just one of those cases. So what we're going to do here in this instance is we're going to take 3.5 inches and we're going to divide that by 1/4. We want to figure out how many of these 1/4 inches we need to make 3.5 inches. So the best way to think about this is basically Give me just a second here. All right, so think about an architect's drawing and figuring out how long something is if it was full scale. So this is the easiest way you could think about it. See if you can translate that to Tokyo. Basically, learn English is fine. Don't worry about that. You're here to learn, so I'm happy that you're putting forth an effort here. Very happy to see that. Because I hope that makes sense there. So that's exactly what we're doing here. He has to draw to a very small scale there. Hey, Neurotic, how are you, my friend? I hope you're doing well. Sure. So a 1/4 of an inch, so it's this number 2 right here, Tokyo. I'm doing very well, my friend. Doing very well. So this is a 1/4 of an inch on a drawing represents 1 foot. Then 3.5 inches on the drawing represents how many feet? So we're trying to figure out, okay, some measurement is equal to a longer measurement. Now we have some measurement here. How long, what would be the measurement based on the proportion that we're given from before? So we have 1/4 of an inch equals 1 foot. So 3.5 inches here will represent how many feet in real life, basically. So when you had maps work the same way, because you obviously can't represent miles on a map without a scale. So it's the same thing. That's why we have to divide this the way we have to. We do 3.5 divided by 4, 1/4. Now in this case here, what are the math things? We're going to talk about uh, addition and subtraction of fractions. We'll talk about decimals. In this class here, we talk about decimals and whatnot. We talk about conversions. We talk about ratios and proportions. So we're doing a lot of those things here. Some of the things that you're doing in your class right now, Legend, is some of the things that we do talk about. In this course as well. So absolutely one of those things that is very important. We do talk about those things that you're probably currently studying right now in some capacity. This particular class for technical mathematics, we cover all the surface topics here. We're going to go all the way up to trigonometry, but just on a surface level, not into very deep down things. But just on a very surface level, everything. Yes. Divide. Don't you keep the flip change? In this case, we have to first change 3.5 into an improper fraction. So in this case, we do 3 times 2 plus 1 over 2. We'll divide that by 1/4. So here we get 7 over 2 divided by 1/4. And then you're correct here. You have to flip and then change. That's correct. So you have to flip the second fraction. So remember, the second fraction is the one that flips. So this flips over to 4 over 1. And then we change this to multiplication instead. I guess I should change this to blue. All right, so this is our changes here. Just learned trigonometry? Great. It's not too bad. Okay, and that's correct, Tokyo. Absolutely correct. Okay, so we reduce our pair of numbers here, as you correctly pointed out here. In this case, it happens to be 2. All right. All right. Excellent, excellent, excellent. And here we're going to get 7 over 1. This is 1. This is 2. Sorry. Probably should do that first. 7 over 2, 7 times 2 times 1 over 1. And that's going to equal 14. And that is correct. So 14 feet is going to be your final answer for this problem. Perfect. SOHCAHTOA is part of trigonometry, but not everything. You're going to learn more trigonometry. There's more things than SOHCAHTOA. Because you can't apply SOHCAHTOA to just right. You can apply SOHCAHTOA to right triangles, but you can't apply it to triangles whose angles are none of other angles are a right triangle. So make it a right triangle. So if none of the angles are 90 degrees, well then SOHCAHTOA doesn't apply. So then you have to use something different. Yeah, sure, of course. Of course, my friend, of course. Okay, are there any questions about division of fractions here? I know I just went over one example here, but what I'm going to do here for next time is I'm going to start right here on section 2.3. So I'm going to pick up where we left off here. I'm going to do another example of division of fractions. I'm going to do another example of division of fractions. And then I'm going to go ahead and do section 2.4, which is adding and subtracting of fractions. So I'm going to stop here for today, as we've done pretty much the majority of chapter 2. So I think we'll be able to easily finish here for next time, and then we should be able to move forward here. This just has the first section has a lot of meat in it, so there's a lot of material in that first section just to get the basics down. But really, it's probably one of the heaviest sections in the book. So today, I know it went a little bit longer than what I wanted to, but I promise you, next time will be pretty short, much shorter than that. So we should be pretty ahead of the curve at this point. So we're in good shape, I can tell you that. Does anybody have any other questions before I call class for today? Can one expect to learn about advanced topics here, college level math, perhaps post grad? Uh, Not in this class anyway. I'm teaching statistics, but I don't know if that's even post grad statistics. Honestly, that's undergrad actually, undergrad stats. Post grad, unfortunately, maybe not on this channel per se, because I teach up to Calculus 1. So I do apologize regarding that. But I'm gonna be, full disclosure. Full disclosure. That's what I've taught for nearly a decade at this point. So unfortunately, I can't give you a good answer there. But yeah, are you a grad student, Neurotic? No, I thank you so much, Neurotic. I appreciate the follow. Yeah, look, I'm sorry that I can't be able to help you more. I'm so sorry. I do apologize. But I do love teaching, and that's why I'm on this platform. It's much more interactive. So, Tokyo, yes, we will meet next Tuesday here at 10 o'clock. Um, so at 10 p.m. Central Time, U.S. 10 a.m. Sorry, that's 10 p.m. What am I, an idiot? All right. Okay, that's fine. Hey, look, I respect that. If you want to learn something new, that's perfectly fine. Did some college with math as my major, but I had to give it a. Oh wow, you could do music there, Neurotic. That's awesome, man. Uh, what do you what do you play? Or you should go back learn. Let me say this, Neurotic. It's never too late to go back and learn a little bit more on the side. I've had students who since I teach community college, I have students who did classes for like 10 years while they were still working their full-time jobs. Oh, digital audio production. Okay. Right on. Fair enough. No performance. Fair enough. Sound engineer. Very nice. So some people work for like 10 years, but at the same time, like, you could still do digital audio production and take a class here or there. It doesn't have to be like I gotta take it all at once. Like, if it's something that you want to do, that'll maybe you say, hey, I'm gonna go get a associate's. Maybe you get your associate's degree, and then you say, okay, I want to get a major in math or something like that. Or you have the requirements already from your previous college experience, and you're like, okay, hey, I want to take it to the next level, but maybe take it one class at a time for a while. You can go ahead and do that. That's perfectly fine. In that regard, if you're doing an undergrad degree for mathematics, I can certainly help you in that regard, 100%. So, um, I can certainly help you with the more advanced courses up to, say, Calculus 1 and whatnot. So that's perfectly fine. I have no problems with that whatsoever. I think, look, I think expanding your horizons, if that's something you want to do, Neurotic, I think that's something that absolutely I would support 100%. Because at the end of the day, you're going to be really happy for knowing just that little extra. So calculus is your dream. Amen. I think if you can understand calculus, man, that's great. Calculus can be tough. Calc 2 is really tough, but realistically, if you're willing to put in the time and the effort, you can do anything. And if it's it's like, even if your career path is you heard Calc is brutal because of trig and Calc 2. Yeah, Calc 2 is brutal because of trig. Yeah, that's true. You have to put your nose to the grindstone for about that. You have sequences and series and whatnot, and the trig can be really confusing. You need to put your nose to the grindstone on that. But you know what? If it's something that you want to do, that's cool. That's cool. I fully support putting yourself in any endeavor. If you love what you do, but you want to do a little bit more, perfect. That's all that matters. I like teaching. I like doing what I love. I love doing this. This is my favorite thing to do in the whole wide world. It's just to teach. It's a privilege to teach. So, yeah, that's what makes it fun. What makes it fun is that I can help people in the future, be better people, be even greater than what they already are. I think that's great. If I can be a facilitator of that, man, that's a good feeling right there. Okay, so I'm going to end off class here for today for 097. So that's the end of the lecture here for today. So we're going to come back on Tuesday for the next 097 lecture. All right. I want to thank everybody who's come out here. Here's the questions you're wondering, by the way. Let me open up that up and I'll answer that for you, my friend. All right. Ah, yes, these questions. Okay. I'll see. What is that one? That's the cube root, right? Oh, yeah, that one's pretty simple. Okay. All right, but I want to thank you guys for coming out here very much. I'm gonna answer your questions here, Kat. What kind of students make me angry? The kind of students that make me angry are the ones who don't want to. Hey, I hope to see you in future streams too, Neurotic. Come by and stop by anytime, okay, my friend? Anytime. If you got a question, feel free to ask, okay? You're always welcome here. Anybody's always welcome here. The people who make me angry are probably the ones who don't care about themselves. Like the people who decide not to help themselves. I'm like, well, why did you pay money for the class if you didn't want to show up? I don't understand. I want you to help yourself. I said, it's not about me or an ego or something like that, Tokyo. It's about you wanting to help yourself. And if you don't, And it makes me sad actually more than it makes me angry because it's like, well, then nobody can help you. You're constantly frustrated because you say, well, nobody's there for me. Nobody understands me. And I'm like, well, nobody can understand you because you're not wanting to help yourself. They're trying to help you, but they can't because you're not wanting to help yourself. And that's very frustrating. And it makes me sad because I'm like, I want people to be better than they are when they walk in. And that can I keep striving, I keep working hard to try and, be sure that people can be in a better spot. That's super important. Now, as for your limit questions here, let me take a look at that here. All right. So let's see. All right. So these are positive infinity and negative infinity at the end of the day. Okay. So at the end of the day, all you need to do specifically is just to see. Uh, there are two ways to do this, Kat. So let's talk about that. Okay. There's two ways to do this. One is by inspection or by graph. Okay. So if you look by inspection or by graph, whichever way you want to look at it, you're going to find your answer for that. So let me go ahead and show off at least the first one here. I'll show off on how that's going to work. So I'm going to bust out my calculator here. This. Fortunately, I actually have a calculator on my thing. Oh my goodness. Oh my gosh. All right. I cannot believe it. Okay. Okay. So let's take a good look here at the first one. So the first one says um the cube root of that. So let's put that in the calculator. We'll actually take a look at the graph here. Um, Graphing this can be kind of a pain on the calculator, but we'll do it anyway. Oh, not like that. Let's hit the math key there. There we go. That's what I wanted. So we have the cube root of, in this case here, let's put that in parentheses, 2 plus 3x minus 5x squared divided by 1 plus 8x. All right, now if we looked at the graph of this, okay, here's the graph. All right, the graph kind of looks like this. Now I know the answer to this question here. All right, so, and yeah, that is the answer to this question. All right, good. What a strange answer, though. Really? Okay. I'm going to guess. All right. So what we want to do here is we want to look at what this answer is going to be. So this is stretching onto infinity. So positive infinity means it stretches over to the right. All right. And you say, all right, well, this is stretching over and it's getting closer and closer to a particular number. And I want to confirm that actually in this case. Just a second here. Yeah, that's fine. Yeah, the back of the book is probably a fraction. So let me see if I'm right about this. Okay, so that is the fraction case, right? Okay. Want to be, yeah, no, wait, no, that's, give me just a second here. Put in the wrong number. This is going to be, that, right? Okay, that's correct. Okay, good. All right. Okay, so let me show you how this is going to work, all right? So you can inspect it by the graph, but unfortunately for the graph here, like some of them you can get away with the graph. Unfortunately, it's not a clear-cut answer. It doesn't go to infinity or minus infinity, but it does head toward a particular number here. You're just not sure what that number is, but it looks like it's heading toward that number there. It gets getting closer and closer to that number. Now, The other way of doing this actually is doing this algebraically and knowing a very important rule. Let's talk about that important rule right now. All right. So in the grand scheme of things, when it comes to these fractions here, and I exit out of that. There you are. Yep. I go back to the paint tool here because the paint tool here is actually going to be the most easiest way to showcase this particular problem. So let me copy this down one more time. All right. Just going to get this down here. Limit as x approaches positive infinity. All right. And here we got the cube root. Why did that come on? I didn't even turn on a game. All right. Anyway. 2 plus 3x minus 5x squared. All right, I'm going to have to turn you off because we're having it. So over 1 plus 8x squared. Okay. So one of the things that we have to take to the bank here is that you have to remember the rule here that the limit as x approaches infinity or negative infinity, it doesn't really matter. It doesn't matter which one, of 1 over x is equal to 0. This will prove to be very, very important in this problem. All right, so the limit as x approaches infinity or minus infinity with 1 over x is equal to 0. Now, this does have an added complement to it. This basically can be expanded a little bit further. How can it be expanded a little bit further? Well, it's not just 1 over x. It's also, say, 1 over x to the n, which is any power of x, is equal to 0. So it could be 1 over x squared. As long as basically at the end of the day, as long as the power on the bottom is bigger than the power on the top, then it's going to head over to 0. All right, so let's put that as a little side note so you remember that and kind of keep track of that in your notes here. So the power on the bottom is bigger than the one on the top. It will equal, limit is 0. Okay? So just pointing that out there here in this particular instance. All right, gonna make that a bit smaller. Austerity's sake. There we go. That's a lot better. All right. All right. So that's incredibly important to know here in this problem. Why is that in this case? Well, what we're going to do here is we're going to kind of refashion the problem. You know, if I do everything on a balanced point of view, just like I talked about algebra, it works here in calculus as well. What do you mean? You're probably saying, well, what do you mean by that? What exactly are you talking about? Well, what if I took every single guy in here? All right, so I took every single guy inside the root. All right, every single one, and I divided it by x squared. Let's say I divided everything by x squared. All right, so that's what I'm going to do here. I'm going to divide everything by x squared. So I'm going to rewrite this like this. I'm going to have 2 over x squared. So I'm going to take 2 divided by x squared plus 3x divided by x squared minus 5x squared divided by x squared. I'm going to divide that by 1 over x squared plus 8x squared over x squared. Okay? So that's what I have here so far. All right? Now, let's see what happens when we go ahead and divide everything by x squared. All right. So this is the cube root still. Come back to the limit here in just a second. So we get 2 over x squared here, plus 3 over x, minus 5. This is all over 1 over x squared plus 8. Now, if we take the fact that the limit as x approaches infinity of 1 over x or 1 over x to the n or whatever is equal to 0, then in effect, if we do it this way, 2x squared effectively cancels out because that's the limit of that is going to be 0. 3 over x will be 0 as well. We could say goodbye to that guy. We could say goodbye over to 1 over x squared as well. We could say, have a great day, sad face. All right, so we can basically just kind of pick apart each part here. And in effect, you have two things left over. You have the limit as x approaches infinity of an actual number. I hope I didn't mix this up here because of the cube root thrown in there, but hopefully I didn't. But this is still the idea behind the problem here. So you have the cube root of negative 5/8, which is a number, by the way. The cube root of negative 5/8. And then this is basically your final answer, because the limit of a number is just that number itself. It doesn't have an x in it. And that's it. Your answer will be the limit as x approaches infinity. So your final answer is going to be the cube root of negative 5/8. Any questions about that, Kat? That is the same. That is the same answer. That's correct. Same exact answer. So basically, let me show you why that's the same exact answer here. Yeah, the back of the book is basically saying what I got. Now I'll show you why, because I have to justify that, of course. I can't just say that without nothing. So, just a second here. I'll show you the algebraic manipulation behind that. Okay, so basically the way it works like this. Is that because you have, so you can start off with the cube root of negative 5/8. So because you take the cube root of a negative number, yeah, if you have to take the cube root of a negative number, one of the deals behind that is that you have a negative number by default. So you can take that negative from the inside of the root and bring it to the outside. And this only applies to odd roots of negative numbers, okay? So this doesn't apply to like the square root of like -1, doesn't make any sense. But when you take like the cube root or the fifth root of something, you can bring that negative to the outside. That's allowed here in this particular instance, okay? So do understand that I'm doing that here on purpose for that reason. Now I'm left with the cube root of 5/8 here on the inside. Now I can split apart based on the rule of roots. I can split that apart into the cube root of 5 and the cube root of 8. Now, if you do the cube root of 5 is just some random decimal number. I have no idea what that is. But I do know the cube root of 8, basically saying what to the third power is equal to 8. Well, the cube root of 8 is equal to 2. So you can see here what I got from my original answer and how we split that up to get exactly what you see there in the back of your book. So we get negative cube root of 5 over 2. All right, cool. Let's take a look at the other problem there. Okay. Yeah. And that is, yeah, that's correct. Okay, that's fine. All right, let's look at the other problem because the other problem has a slightly different look to it. So let's take a look at that. Okay, so in this case here, I'm just going to copy this down here. The limit as x approaches negative infinity, all right, of the square root of 5x squared minus 2 over x plus 3. Is have to take care of that flickering second here. If we have a issue here. Why are you having issues with? Not sure why it's flickering right that. See if I have to change that in my settings for my monitor. Sorry about that. All right. In any case, all right. Now we're gonna do the same technique here. Minus 5, but 8. Minus 5, but 8 is not minus. Minus can go. Okay, so minus can go on the outside. It's okay, Tokyo. Don't worry about it, buddy. Are you from Japan, Tokyo? Mongolia, okay. Respect, man, respect. I can totally respect that. All right. Let's see here. How do I want to state this? Okay, yeah. So the negative or odd can go on the outside. It is a rule only for odd, like the third. There we go. Oh, yeah, that's right. Okay. So Tokyo, you must be in So you must be in Ulaanbaatar. Is that where you're at? Because I know that's the capital city of Mongolia. Or if you're in another city, it makes sense. All right. Well, I'll let you tell me in just a second. All right. In any case, um, okay. So for the purposes of this particular problem here, we're going to go ahead and do the same thing as what we did in the last problem, where we divided everything. In that case, we divided everything by x squared because that was the highest power. In this case, I'm going to divide by the highest power here, but it's not as obvious as it looks when you take a look at the problem. In fact, what are we going to divide by here? What is the highest power in this case? Well, the highest power in this case, in this instance, the highest power in this instance is x. That is correct. All right, so the highest power is x. It's not so much as because of the bottom power, though. It's actually more, it's not because of x plus 3. You could say, some people say it's x squared, but that's not true. But you do have to make an adjustment because it's inside a square root. Okay, so I do want to point that out here, Kat. That is very important. The highest power is x, so I'm going to divide by x here, but maybe not in the way you thought. So I'm going to have to rewrite this. Like, I'm going to come back to the square root here in a second, but I'm going to take x. If this was x to the fourth, for example, like 5x to the fourth instead of 5x squared, then you would have to divide by x squared and not x. It actually does matter at the end of the day. So I want to point that out there. That's got to be really careful about that. Yeah. In these cases, the problems that you're going to encounter in this class, you're probably never going to run into that situation. Well, maybe you may run into it maybe once in a blue moon, but yeah, you can't assume that it's always going to work out that way in every problem. All right. So we have x over x and 3 over x. We divided by x here. But underneath the square root is where things are different, and this is why it changes, okay? So pointing this out here, this is where things change quite a bit, okay? So what we get here specifically, what happens here in this case? We get 5x squared, we get minus 2. Now we're going to divide each of these here, but since this is underneath the square root, and since we're dividing by x, if we place this x inside the square root, this suddenly needs to become x squared. Okay, so now that becomes x squared instead. You actually have to double the power because if you're dividing by x everywhere, for example, well then if you place it inside the square root, that has that power has to now double as well. So in order to split that apart, correct. Because the square root canceling being it up to the squared, that'll make it x at the end of the day. That is correct. No, you were right the first time because the square root canceling will cancel. So as you know here, like the square root of x squared here, right, is equal to x. So that's why we divide by x squared. So you were correct the first time there. Okay. Okay. Well, let's take a good look here at the rest of this problem here. All right. Oops. Need the marker there. All right. So let's clean this up a bit. So we get 5x squared over x squared. That's 5 minus 2 over x squared. That didn't change. Over 1 plus 3 over x. Now, once again, we're going to use the idea that the limit as x approaches infinity is going to be as limit as x approaches infinity of 1 over x, all right, is going to be 0. So 2 over x squared, that's going to be 0. And 3 over x, that also is going to be 0. So this leaves us with our final answer of the square root of 5 over 1, or just the square root of 5. And there we go. Bam. Got it. Gotta love final answers when they all come together. Any questions about that? I hope that made sense now. Ooh. Hey, gamey, me. Hey. Tuesday's topic will be limits. Maybe not. I think that'll be more on the fraction side. Uh, what is this? This is Calculus 1 talking about limits here. Nah, it's not too difficult. Yeah, the approach is always the tougher part. I agree with that. The calculation isn't too bad, but it's really the approach. Absolutely. At times it can be pretty top heavy. Yeah. Let's not lie. What is a calculation? A calculation is where you put a few numbers together and figure out what you need to find using operations at hand. Where when you figure it out, it's easy. Yeah. It's like the derivative. Like you do it the long way at first, and then when you do it the short way, you're like, man, okay. Okay, take care, Gaty. Pop in, pop up, a bam. Yeah, right. That's exactly correct. Long and synthetic division. You like synthetic division. However, the bad part about synthetic division is that you could only work with it in a very limited context. That's the bad part. So, all right. Any other questions, anybody? Before I head out here for today, I hope I was able to help. That's all that matters. Hey, man, of course. You know I'm here to help you anytime, okay? If those are your local times, yes. Hey, no problem, man. No problem. I have on Tuesdays I have one class Tuesday, Thursday, one class Tokyo. Oh yeah, that's on Mondays and Wednesdays. Yes. Actually, yeah, you'd be a day ahead. That's right. Yes, that is correct. I teach 3 classes on my Mondays and Wednesdays. Isn't that hard? I don't find that. I've been used to it for a while, so teaching 3 classes in a day isn't too bad. At first, I thought it would be tough, and then it does take a lot of energy out of you at times. But you know what? You do it for the love. That's all that matters. All that matters. No, actually, they're not. They're all on statistics. So for this semester, anyway. Last semester, I think they were all on the. Yeah, so I have 2 classes that are the same, and then the other class is also a stats class. Uses the same book, just works a little faster than the other one. So yeah, everything's an online class at this point, Tokyo. It's the coronavirus pandemic stuff. So nobody's allowed to go back to the campus until the pandemic is over. Do you progress every class when there are 3 classes in a day, or do I teach the same topic? I teach the same topic in those classes. Like one progresses a little faster than the others because that's a more advanced course. So they're both again they use the same book, but because one is more advanced, I tend to progress a little bit faster than the other two. But that's just appropriated for that one class, in all honesty. Yeah. Um. Yeah. I mean, I think I've had semesters where I've taught 3 different classes. Yeah. I teach at 2 different schools. Uh. Yeah. Yeah. That's right. Um. But yeah, I teach at 2 different schools, so like I've had years where I've had 6 different classes, all together with 6 different preps. So, and you get used to it after some time. And it's really not too bad. It can be daunting at times, but I think like six is kind of like my limit I can teach in a given semester. So doing 7 can be pretty tough. but I think 6 is like my limit, which is pretty good. So yeah, so I have yeah, so Saturday, Sunday. So for me, Saturday for on your Saturday, Sunday, Monday, Tokyo, yeah, Tokyo, yes. Okay. For your Saturday, for me, it's Friday, Saturday, Sunday. That is correct. Check there. That is okay. Okay, I like this. All right. Any other questions you guys got? You guys, that's why I use. Yeah, that's right. I use Twitch just for that. So, all right. Um, you're gonna subscribe to my YouTube channel. Oh yeah, you can subscribe to my YouTube channel. Sure. I mean, I have an archive of a bunch of videos which I'll have to put up this weekend. So, yeah, you can go ahead and subscribe. I mean, it's just there for archiving my videos and stuff. So, I mean, they're just basically the same VODs and lectures that I post here that I do here in class. So, yeah, you can absolutely, if you like to, it's totally up to you. We sometimes visit entertaining, like how Archimedes calculated the circumference of the Earth. I mean, we can way back. It's kind of like way back in the day replay. Archimedes, man. Like if we had Archimedes today, Archimedes would still be the smartest man on Earth. Archimedes was incredibly intelligent. Like that guy is so like. I wish I could meet Archimedes in real life. Because it's just I don't know, man. He invented so much, and he made great strides for not just the field, but let's not talk about the field of mathematics, but in practicality, like you know, irrigation basically was transformed thanks to Archimedes' screw. I mean, you literally changed the entirety of an entire civilization based on an invention based on mathematics. That's absolutely amazing. So can't really argue with that. The man's a legend. So man is a legend. All right. I mean, I'm pretty sure that ancient scientists and mathematicians would be very impressed about how far that the field has gone. Considering, math has been stretched out to very far limits. And I mean very far limits, probably more so than other fields, other scientific fields. I mean, math is probably the oldest scientific field um, to date. So, where we haven't, we know exactly how far we can stretch, and we can stretch just a bit further than that. So, um, my favorite contemporary mathematician, yeah, I have to say it's Archimedes. Like in all seriousness, it's yeah, and in all seriousness, it's I would say Archimedes is my favorite ancient mathematician. Um, you could say Euclid's pretty good too. Uh, I would say those are my two favorite mathematicians. Or you can make an argument for Euler as well. Oh, mathematicians that are living and working today. Yeah, I don't know too many. Well, I mean, I know that of course, my mentor back in college. I could say I like him. But yeah, I've been so focused on teaching, I don't keep up with like the mathematicians in the field necessarily. But those people who are working hard to stretch the field further, I totally respect what they do. I think that's awesome. I know that seems like a big cop out answer, but the end of the day, I'm just trying to help people, just to educate them. Necessarily, those people are actually making the strides and pushing the scholarly goalposts. You know, I think that's, and I respect them for that very much. Trust me on that. So, educate calculus. All right. All right, gentlemen. This is where I'm going to end off here with my stream for today. I'm going to go get some lunch. So, I'm going to go have some lunch. But I want to thank you guys for coming out here to my stream once again here today. I'm going to be back here. I'm going to be back on Monday teaching my stats classes. I'll probably be streaming tomorrow for my friend for probably some algebra stuff. But in any case, thanks guys for coming on out. Come on back anytime. You guys are always welcome to come on back. I appreciate your time. I appreciate your effort. Uh, love you guys very much. Thank you. You have a wonderful day as well, Tokyo. I hope everything in Mongolia is well in Ulaanbaatar. All right. All right. Thank you very much, everybody. Have yourself a great one, and we'll see you later. All right. Take care, everybody. All right.